So this is the second lesson of chapter 1. We're going over the slope of a tangent. So we're just going to go over some definitions so you know what these things are. Right here we have a quadratic function or some type of parabola. Okay? And these red lines off of it are lines that are tangent to it. A tangent line touches but does not cross the parabola. Okay? So it touches at a specific point. And of those tangent lines, we can discover their slopes. Because they're linear or straight lines, the slope will be the same all the way across the tangent line. So what that means is the point where it's touching this curve, our rate of change will be the same rate of change anywhere along this tangent line. So if we can find the slope or the rate of change of the tangent line, we can find the rate of change at this specific point in the curve. This isn't the rate of change throughout the whole curve. It's just at that one point. So at this point, if we found the slope of the tangent, we could get it here, and we could do that for numerous amount of points. In fact, it's infinite. There are so many different rates of change across the curve. We really only look for specific points. Okay. When doing that, okay, so those are tangent lines. It's also going to bring us to a little definition of a secant line. So secant lines are the green ones we've drawn here. And secant lines, they cross through our parabola. Okay. Secant lines are going to help us get the idea of how to find the rate of change at a specific point. So a secant line, a lot of times these will be used for average rates of change. I don't know why I'm looking up there. So an average rate of change, I'm going to zoom in a little. That's better. An average rate of change, think of it as we're at point P, and then they ask us, what would the average rate of change between point P and point Q be? Well, there's all these rates of change from P to Q along the original curve. Okay? So from P to Q, we have millions and millions of different rates of change. What we're trying to find for an average rate of change is this from P to Q. So we have a linear function going from those 2 points. That gives us an average between the two. Okay? And as you notice, we've started moving the secant lines flatter and flatter until they look like eventually a tangent line. Okay? So what that's saying is we can change our secant lines or our rates of change to be less and less. So eventually, because if you guys notice, when we're doing rates of change or slope, we need 2 points, point P and point Q. Makes it really easy to solve depending on what line we're on. But when we get to a tangent line, only one of the points is touching the graph. Okay? So we're going to show you the formula in a minute. I'm sure you guys have seen it before. Our formula refers to an instantaneous rate of change. And what that means is it's almost as if we're expecting our average rate of change to be between point P and an infinitely small number or movement along the x-axis. Think of it as something like going on till 1 and even greater than that. Okay? And the reason we think of it this way is because such a small change won't give us a big change in numbers when we put it into our formula. And we'll show you what I mean by that. We'll actually input this in for, well, I might as well show you the formula now. Our formula down here. Our h is going to stand for our limit as it approaches 0. And what we mean by approaches 0 is it's not technically 0. It's a number that's infinitely small that is very, very close to being nothing. Okay? And what we can do is, as we go through some of these examples, we'll actually plug in a different value of h, something that's infinitely small, like that number I'd written above, just to show you that it's an approximation. The approximation will be very, very accurate, but won't be perfect. Okay? So when we talk about rates of change, we're talking about the change in the y-axis over the change in the x-axis. If you guys remember this from grade 9, even in our vectors, we talked about it. That is our y2 subtract y1 divided by x2 subtract x1. Okay? Now if you remember with our secant lines, we had point P, which is where we were trying to start from, all the way to point Q. Point P is whatever number we're at, so say we're the number 4. That would be the x value. the y value, we'd be plugging the number 4 into whatever the function is. So we had a quadratic. I know it wasn't a normal quadratic, but we'll say it's x squared. Okay? So a would be 4 in this case, and our y coordinate would be plugging the number 4 in for x. So 4 squared gives us what number? 16. So in this case, we'd be looking at 4 and 16 as our point P. Okay? And our point Q has to do with our rate of change. Now our point Q we actually had numbers for. So A again is still the number 4. Now H. Had I done one of the first secant lines, so we'll zoom out a little. There we go. Had we done one of these secant lines way out here, we'll say that our H value is a new point. Maybe it was 8. Okay? So we have 4, what do we got in there? Plus 8. And then we'd have the function of 4 and 8 put together. Okay? So as we go through these, our numbers are going to get less and less. And that's where we're getting to instantaneous rates of change, where our H is going to be an infinitely small number that it essentially becomes just the number 4. Okay? Our formula is down here at the bottom. We'll zoom in again so you guys can get it. I know this is all theory. We'll get into some of the numbers after. Okay? This is the major formula you guys need to know. Okay? Now technically, this part here is this with our A, F at A plus H, and F at A plus H plugged into our coordinates and simplified. Okay? And what we'll do is we'll plug this in our first example so you guys can see what I'm talking about when I say I've plugged these values in. Technically, these values here are this is our x, so I think this stands for x2, y2, and x1 and y1. And these values have been plugged into our slope or rate of change formula and then simplified to this. So this is the one I really need you to remember. We're going to try to explain it as we go through this lesson and how we derived it or how we got to it. And we'll go through a couple numbers in the next one. So let's jump to another page. First example. Okay. Okay, the very first example, it says determine the slope of the tangent to the graph of the parabola f at x is equal to x squared at point P. Okay, and P is at 3. And they've even given us our y. They didn't have to. They could have just said 0.3, but they've given us our y value. Okay? So what we're looking for here is we're going to use our points and the formula we had at the bottom. Now, if you remember, we're looking at, now in your textbook, if you look at the very first example, they've made an error in the symbols. They put change in x over change in y. We're working with change in y over change in x. If you have a pencil, you can correct that in that textbook if you like. It's the very first example. They made a little error there. Okay? And we know change in y over change in x is y2 minus y1 over x2 minus our x1. Okay? Now, what we're going to do is refer this to a secant line. A secant line, remember, was our q, and our formula for that was a plus h, and the function of a plus h. Well, we have an a value here. Our a value is 3, and 9 is the function of a. When they plugged 3 into this equation, 3 squared was the number 9. That's what our y coordinate was. So our a is 3, and our f at a, or the function of 3, is 9. Our q, a plus h, and the function of a plus h. That's going to represent our y value. Well, we can actually plug numbers in for that also. If you guys notice, our q is then going to be 3 plus h. Okay? And the function itself is a squared over our x. So what we're going to do is we're going to replace our x, and of course we're going to replace our a with the number 3. 3 plus h. Okay? That 3 plus h is going to replace our x in any function. That's why they use the f function and why we needed you guys to take advanced function. So you're used to plugging in values in these mathematical symbols. So whatever the function is, it could be a root, a radical, a cubic function, numerous types of functions. what you're doing is you're plugging in your a plus h in for the x value of it. Okay? So in other words, what's going to happen here is the y value of q is going to be 3 plus h squared, because that is what that function is. We have a quadratic, we're squaring it. Okay? So all I've done here is I've replaced our x value, this used to be x, with 3 plus h, right? And that's what the original formula says, a plus h. Well, our a value was 3, so we replaced a with 3, and we replaced our x with a plus h. Now, we're going to plug this in the formula. I want you guys to notice, okay, this is our y2, not a y, x2, x1, y1. I'm not sure why that was so hard for me to write. Okay? So what we're going to do now, we'll highlight them so you guys can see similarities here. Here's my x1. I'm going to replace my x1, y1, y1, x2, x2, and y2, y2. We're going to plug these values into our formula. When we go to plug it in, we're left with 3 plus h squared. Our y1 is negative 9 divided by x2, which is 3 plus h, subtract x1 is the number 3. Okay? So this is still the change in y over the change in x. We're finding what the change in y and the change in x, so the rate of change at the point 3 and 9 is right now. Okay? So we're going to simplify this now. First of all, if you guys look at the bottom, I have 3 minus 3. They create a 0 or cancel out, as a lot of you guys would call it. And we're left with just h on the bottom. Now I want to start to refer this point specifically back to what we had. Okay, I didn't simplify the top yet because I want to refer this back. Or 3 plus h squared minus 9. If you remember the formula we had written on our other page, okay, we had our formula stating, let's bring it up for you guys, to a page. At the very bottom, okay, we had the function of a plus h minus f at a divided by, let's see, h. Okay? And what I'm doing is I'm referring to our formula at the very bottom of the left page there. Okay? If you notice, and we're going to zoom back in now. If you notice, there's similarities between these two. Because this is the simplified version. That's why we use it. It's the simplest one. What we actually did is we started from the very beginning. Okay? We could have went straight to this formula here. But I just wanted to show you guys how they derived that formula using numbers. That a plus h, well, that is our 3 plus h, remember? So we've plugged that in. And our function was a power of 2. So we put our 3 plus h to the power of 2. So that is the function of a plus h. And we subtracted f at a. Well, f at a was our y coordinate when we plugged in the number 3 into it. And then we got the number 9. So that's what our f at a is. And again, we only have h at the bottom where they have h at the bottom. Essentially, our 3's here cancel out every time we put this formula in. So if we were to start here, every single time we'd be forced to cancel this all out. There's really no point. We're going to end up here. So from now on, we're going to use this formula when going through it. Okay? So, again, we're going to keep going here. I'm going to expand my brackets. That's going to give me h squared plus 6h plus 9, subtract 9, divided by h. Okay? Now I'm going to drop the brackets off of the top. When we drop the brackets off, we have h squared plus 6h plus 9 minus 9 over h. Well, positive and negative 9 are going to give us what? 0, right? So we got a 0 here. I'm then left with h squared plus 6h divided by h. I can factor the top of this. I have an h in both of the two terms. So we're going to factor out h, and we're left with h plus 6 divided by h. And now that I have a multiple, or a number we're multiplying by, of h, and we're dividing by h, what do these two h's do when they're divided by each other? Cancel or make what number technically?
1.
1. Good. I want to make sure you guys understand that idea. So they make a 1 or cancel out, and we're left with h plus 6. Okay. Now this is where we get to our point. Now, because normally we're going at the limit of 0, even though I haven't written it in this question, we're usually using the limit as h approaches 0. So we're getting to an infinitely small number. Normally what they do is they just substitute 0 in for h, and they'll say the rate of change at this point is the number 6. Okay? Because if h is 0, well, 0 plus 6 gives us 6. I want you to think of that idea. Is technically we're using an infinitely small number. We're not using 0. We're using a number that is extremely close to 0. So I know I don't have a lot of room, and I know you guys understand the idea that it could go a very, very long time if I write numbers, but let's plug in something like this. Okay? And remember, sometimes we talk about rounding. Well, let's say that's what h was, infinitely close to 0. You can get much, much closer than that. We're going to plug that value in for h, okay? So instead of jumping straight to 6, we're going to go down here. And our h value is 0, a whole bunch of these here, okay, plus 6. Well, we're going to get 6 point, okay, 1. And really, in terms of a number that matters, I know you guys talk about rounding, we shouldn't always round, but in terms of a number that matters, what essentially is this number as a rate of change? Anyone know? This number, 6 point, many zeros in 1, can approximately be what number? 6. And that's the idea of h. Okay? The idea of h is it's not 0, but it's approaching 0. It's an infinitely small number. Well, when we conclude and put that infinitely small number attached to 6, it's really just the number 6. Okay? In terms of values that matter to us. Okay? So that's the idea of our h when we're going through this. There's our 2 pages. We've gone through one example, and I've showed you how they kind of derived the formula.